This installment, we're going to look a little more in depth as to what we mean by simple harmonic motion. In a previous lesson, we introduced this. We spoke about changing acceleration when the speed is changing. So we have some acceleration that is changing. It creates an oscillating motion, so there is jerk involved. And of these two types, where there is a constant period or a changing period, we are focused on the constant period. And so if we have this relationship, omega is 2 pi over t. If t is constant, that means omega is constant. So in this sense, it's like constant velocity. In this case, it's constant angular velocity. And so we have some examples. So the first thing is, we want to know, do which ones have a constant period? That's what must happen. It means there's a constant omega. And how can we tell is an interesting question we're going to get at when we look at a few examples we'll study. So one example is a horizontal spring attached to the mass, to a mass. And it's hard to visualize, almost impossible to create, but if we imagine an air track with a mass on it attached to a spring that can both compress and stretch, it would be that moving back and forth. And we'll talk about that in depth. We could take a spherical bowl and put a ball or a marble inside it and release it at the rim, and it would go across the bottom and back up the other side and back and forth, much like a pendulum. Or we could take an object floating in a body of water, let's say a buoy, and we come up next to it in a boat and we push down on it and hold it there and release it, and it will bob up and down in the water. Like the horizontal spring, we could do the same thing with a vertical spring. And for musicians out there, and this is I find a very, very helpful one, a plucked instrument string. So if we have a guitar string or a ukulele or banjo or violin, that a string will have a certain length. If you pluck it, it will have a constant frequency. And the string itself will vibrate back and forth between two states, back and forth. And so it oscillates back and forth too. And since it has a constant note, that tells us that the period is constant. Diving board, a diver is on a diving board. They go out on the end and they jump on it. And if they get out there and they get at a stable height and just keep bouncing back and forth at that stable height, well, that's going to be simple harmonic motion. As will the case be if they change their height. Same thing for a trampoline. We can imagine an airplane, someone tweaking the edge of an airplane, or as it's traveling quickly, some turbulence in the air could set it in motion, and the wing could vibrate up and down. Tree branch. If a tree branch is vibrating back and forth in the wind, or a skyscraper. It turns out that skyscrapers like the World Trade Center, they might move by almost 2 meters in the wind. The top may move that much. That's like 6 to 7 feet. So there is a little bit of a significance of a constant period. A stroboscope is a flashing light. And the delta T of the flash is constant. So if you get the right period, an object that is oscillating, say, between these two extremes back and forth, if you adjust that stroboscope so that the delta T matches the period of that thing, when you look at it, this moving thing will remain motionless. So vibrating things, when they are matched with a flashing light of the same period, will appear to be motionless. And so we could see this sort of thing happening with waves or anything at all that's vibrating. And they use stroboscopes to do the timing on an engine that the pistons fire and so forth. So this is an example this is an overview of the different kinds of examples. And we are going to spend quite a bit of time over the next couple of installments looking at horizontal springs attached to a mass.